In this video, let's take a look at area and volume. The first thing is the area between two curves. It says if you're integrating with respect to x, then the area between two curves is from some lower x boundary to an upper x2 boundary of the integral of f of x minus g of x, where f of x is the top function, g of x is the bottom function. If the top or bottom function is not consistent throughout the boundaries of the integral, then you must split up the area into two or more integrals. If you're integrating with respect to y, then the area between the two curves is from some y lower boundary to an upper y boundary of f of y minus g of y dy, where f of y is the right function and g of y is the left function. And here's our example. Find the area of the region bounded below by the piecewise function. So you have this function on the top, and we can see that this rational piece is this part, and then we have a linear piece, this part, and they have their boundaries between 1 and 2 and 2 and 4. And then the lower function, the g of x function, is this quadratic right here between, again, 1 and 4. So then the area would be the top function, which is the rational function, between boundaries 1 and 2 minus the lower boundary, which is the quadratic, dx, plus between the boundaries of 2 and 4 of the linear minus the quadratic dx. When we revolve around an axis, this is our volume of revolution. So it says volumes of revolution can be obtained either by rotating a region around the x or y axis. If you rotate around the x-axis, you need to integrate with respect to x. If you rotate around the y, then you need to respect to y. You can also rotate around just some random vertical line or horizontal line, so it doesn't have to be one of the x or y axis. Two methods. The first one is the disk method. If your representative slice through the rotated region does not have a hole, then this is called the disk method, and that, of course, is just a circle. So the volume is just the integral from some lower boundary a to an upper boundary b of pi r squared dx. And since pi is just a coefficient, you can pull that out front. The washer method is if your representative slice through the rotated region has a hole in it, then you use the washer method. And so you have a larger radius, and you're going to subtract the smaller radius. So the larger radius minus the smaller radius. This is like the big R and then little r here. All right, here's our two examples. It says for the disk method, the region R lies in the first quadrant, bounded by the x-axis, y-axis, y equals 2 to the x, and x equals 3. Find the volume of the solid generated when R is rotated about the x-axis. So I went ahead and graphed it just so I could get a visual of it. And here it is. And I'm going to go ahead and erase that disk. Sorry about that. Can't seem to let it expand. All right, it's fine. So we can see that here's our top function. This is the 2 to the x function. We have y equals 0, which is the horizontal axis, x equals 0, the y-axis, and then this x equals 3. When we rotate this around the x-axis, we have this circle. So here's our radius. Our radius is just found by the 2 to the x minus 0. Okay, and so now let's see if I can get it to, there we go. The volume is then just pi times the radius r squared between 0 and 3. All right, in the washer method example, it says we have a region bound, lies in the first quadrant, bound by the x-axis, the y-axis, y equals e to the x, and x equals 3. Find the volume of solid generated when r is rotated around the y-axis. So here is my graph. And now there is a little section here at the bottom between 0 and 1 that if we were to, that is just a solid, right? So we are going to have just some circles down here. Let's see if I can, these when we rotate are just going to be that solid. So you'll have an integral between y-axis of 0 and 1, and that is just going to be generated by the big R, which is just 3 minus 0. And then from 1 to e, I believe, or whatever our top function is. Let me see. Yeah, y equals e to the x, sorry, your top function. Here's how your radius, you're going to have the big radius, which is 3 minus 0, and then your inner radius, which is that e to the x minus 0. Okay, so there's your visual. Let's take a look at the equation. So it's pi between 0 and 1. I told you that was the piece at the bottom of just the large radius squared, dy, plus pi between 1 and e to the third. And I guess, okay, and that's just going to be the outer radius minus the inner radius. The inner radius is created with that natural log y squared dy. Okay, so where did the natural log y come from? Well, we need to go ahead and solve this for x. And so if I have e to the y is equal to e to the x, if I take the natural log on both sides, that's going to give me x is equal to natural log y. When you're integrating with respect to the y-axis, it needs to be in terms of y. And that's where this guy came from. Okay, so volumes of known cross-section. The situation occurs when a region is filled with geometric shapes. We work with squares, triangles, semicircles that are perpendicular to a region. The dimensions of the cross-sections are determined by the functions that bound the region. And so the volume is from some integral from a to b of the area dx. And it says a of x is the area of the cross-section. If the cross-sections are perpendicular to the x, integrate with respect to the x. If the cross-sections are perpendicular to the y, integrate with respect to the y. The region R is bound by the x-axis, x equals 1, x equals 3, and this cubic function. Region R is the base of a solid whose cross-sections are squares. Okay, so here's my picture. See if I can get it to expand. All right, so here's their cubic function right here and our boundaries, and we can see I tried to draw in some three-dimensional squares. So each side is created by the cubic function minus the x-axis, so it's just minus 0. So the area of this square is just going to be side square. And so then the volume, let's see if I can get this to small again. Okay, so then our volume is going to be from the lower to the upper limit, from 1 to 3, of the side squared dx, and that'll give us